Our work is ExtraNeRF, visibility-aware view extrapolation of neural radiance fields with diffusion models. Given a few captured photos as input, we can reconstruct a NeRF. However, when rendering images from extrapolated viewpoints, we perceive significant artifacts in those unobserved regions. To address this issue, we propose ExtraNeRF, which leverages supervision from our modified diffusion models to complete unobserved regions and significantly reduce artifacts. Here, we introduce our pipeline step by step. In data preprocessing, given n input images with camera poses, we use SPARF to acquire the depth maps. In step 1, using images and depth as supervision, we trained a NeRF. In step 2, we train an in-painted NeRF. To do so, we initialize an in-painted NeRF with the weights from step 1. Next, we use an iterative optimization approach to optimize the in-painted NeRF. In each iteration, we sample one virtual view. Render an image from that view. Estimate a visibility mask from that view using the NeRF in step 1. Feed the image and visibility mask to the RGBD inpainter. And in-paint image and depth map. We then use this in-painted image and depth map to supervise our in-painted NeRF. In addition to in-painted supervision, we also use supervision from input images and depths. We iterate this optimization through m different virtual views repeatedly. In step 3, we adopt the same optimization approach, but replace the RGBD inpainter with an RGBD enhancer for the supervision. Here, we describe our RGBD inpainter and enhancer in detail. From a virtual view, we render an image and depth and estimate a visibility mask. We use the diffusion inpainter to in-paint the color of pixels in the visibility mask and get an in-painted image. Next, we use the in-painted image as guidance to repaint and complete the depth values in the visibility mask using our depth completion model. Finally, the in-painted image and depth map can be used to supervise our in-painted NeRF. We utilize this process again in step 3, diffusion-guided enhancement. The difference is that we replace the in-painted NeRF and diffusion inpainter with enhanced NeRF and diffusion enhancer, respectively. Here, we show the images rendered by NeRF from a virtual view at different training stages. In step 2, diffusion-guided inpainting, we obtain plausible but blurred content from NeRF after several hundreds of training iterations. In step 3, diffusion-guided enhancement, the blurred content in NeRF is supervised by the diffusion enhancer, and the rendered image contains more detail after hundreds of training iterations. Here, we describe the way to estimate visibility mask. In the pipeline, we need to estimate the visibility mask for each virtual view. Hence, we describe how we estimate visibility mask in detail. For illustration, we visualize the 3D scene of a certain row of an image from the bird's eye view. The orange triangles are input views, and the red triangle is the virtual view. We shoot out a ray from the virtual view and sample a point on the ray. At that 3D point, we calculate its visibility to one of the input view using the transmittance between that 3D point and the input view. We calculate the visibilities for all input views and aggregate the list of visibilities by taking the kth largest value, where the value of k is 2 in this example. We perform the same calculation and obtain visibility for every point on the ray. Next, we collect the visibilities of points on the ray and fuse them through volumetric rendering with blending weights along that ray. The output value indicates the visibility of this specific ray and pixel from the input views. We use a threshold of 0.5 to binarize it. If the value is larger than 0.5, this ray and the corresponding pixel are visible from the input views, otherwise they are unobserved by the input views. In this example, the ray and corresponding pixel are identified as not visible or unobserved by the input views. We perform the aforementioned process for every pixel in the virtual view and record the value on the image. Along with the rendered RGB, we can acquire a color image with a visibility mask in the virtual view. By using a larger value of K in the aggregation function, we get a larger mask area. This is because pixels outside the mask region need to be visible by at least K input views. We set K equal to 2 since the minimum requirement for the number of views for 3D point triangulation is 2. Here, we describe the way to collect data for the diffusion enhancer. To collect data, we perform a variation of Step 2, diffusion-guided inpainting. We create a pseudo-visibility mask in each input view, and do not use supervision in the mask. Additionally, we create pseudo-visibility masks in virtual views, and use inpainted pixels in the pseudo-visibility mask to supervise inpainted NeRF. The pseudo-visibility masks are created with the following 2 steps. First, by using a larger value of K in the visibility aggregation function, visibility masks become thicker. Second, we dilate the boundary region of the mask. Here, we show some examples of the corrupted data. The pixels are blurry within the mask due to inconsistent supervision from the RGBD inpainter. To fine-tune our diffusion enhancer, we randomly select some corrupted images and pair them with corresponding ground truth captured photos.